Let me take you on a journey to the coldest place on Earth and its last and greatest wilderness, on a voyage to Antarctica. Hello and welcome to A Voyage to Antarctica, brought to you by the UK Antarctic Heritage Trust. I'm Alok Jha. With Antarctic sea ice levels reaching record lows for the past 4 consecutive years, my guest today is world-renowned glaciologist Professor Martin Siegert. He'll talk to us about glaciology, the study of ice in all its forms, from the Antarctic ice sheets and glaciers to the icy bodies in our solar system, why it matters, and the crucial role that ice plays in our climate. Martin is a Deputy Vice-Chancellor at the University of Exeter. Previously, he was a professor at Imperial College London and director of the Grantham Institute. And before that, he was head of the School of Geosciences at the University of Edinburgh. He's published more than 250 papers and 8 books on the geophysical exploration of Antarctica. In 2013, he was awarded the Martha T. Muse Prize in Antarctic Science and Policy, and in 2007, he was elected a Fellow of the Royal Society of Edinburgh. Can you pinpoint a moment when you became interested in the Antarctic? What was it that sort of brought you to this point, or began your journey to this point?
Yeah, there was a real moment, actually. I come from a very non-traditional background when it comes to university. First person in my family to go to university. Went to an ordinary comprehensive school with very little expectation of the sort of students that went there. My parents didn't go to university or anything. I didn't do A-levels, right? So it was all a bit of a mystery from O-level onwards. Now, I was really interested in the world around me as a teenager, and I was pretty good at maths as well. And so I came across a program called geophysics, which I'd never heard of before. And I had no advice about whether it would be good for me, but I just took a chance to do it. And it was one of the best ideas that I had, turns out, but also a problematic one as well. Problematic because in the 1980s, people doing geophysics largely went into the oil and gas industry. And I knew even at that stage that that's not what I wanted to do for my life. So I was trained up to do oil and gas exploration, but with no interest in doing it. So I had to find something else. There was a death in our family, quite sudden, pretty awful. And I took a year off after completing my degree. And I worked in road construction. So I was a labourer on road construction in a bypass around a village in Suffolk when I was 21. And I was thinking that I don't want to do this for the rest of my life. It's really hard work, right? And someone advised me that a PhD would be a good idea to consider. So I think we got to about sort of March, April of the year, around that time. And I was sitting in a hut at the side of this newly built road, and the rain was slamming on the window. I do remember it really well. And I had with me a new copy of The New Scientist. And I just happened to go down to the newsagents that day and pick it out. And I was sort of thumbing through the job adverts. And there was an advert for a PhD position in glaciology. And now I knew nothing about glaciology. I hadn't studied it in any way. But what the requirements were was someone who is good at maths, good with computers, and has a geophysics background. And that was me. That's what I was doing. So I applied for it and I got it. And everything happened as subsequent to that moment, really. So on the side of the road, on a bypass in Suffolk, a hut that's no longer there, there was a day in March or April 1990, I guess, where my life changed.
Well, from there to one of the world's authorities on glaciology is quite a journey. For people who might not be familiar with what glaciology is now, in the way that you weren't when you applied for that PhD, give us a nutshell. What is glaciology?
Well, glaciology is the study of ice in all its forms, and that includes the glaciers in the mountains in Switzerland, all the way to the massive polar ice sheets of Antarctica and Greenland. It involves the floating thin ice over the Arctic Ocean and it involves even permafrost as well. So glaciology is an encapsulation of all things related to ice on our planet, and indeed other icy bodies like on Mars and in Europa, one of the orbiting moons of Jupiter. Glaciology is a very eclectic, diverse science, and it includes the analysis using things like geophysics, which is what I do, numerical modeling, field observations, satellite data, laboratory investigations. It gathers all of those things. The only thing that it has in common, of course, is the study of ice.
Okay, and of course, glaciology is, when you describe it like you have, the study of ice. But I want to talk about the history of this first, if you don't mind. Can you talk to me about how the work you're doing now, the research into the ice, how does that link to the sort of initial explorations that people like, Captain Scott and others were doing in the beginning of the 20th century?
There really is a legacy, actually. So when we look at the early explorers in the heroic age, if you like, especially from the United Kingdom perspective, it was really driven by science. So it was about exploring and the race to the pole that people know about. But the thing that distinguishes the effort from Shackleton and Scott compared with Roald Amundsen, for example, Amundsen was really focused specifically on getting to the pole, whereas Shackleton and Scott's expeditions were interdisciplinary, multidisciplinary, involving emerging subjects like glaciology, but also meteorology, biology, geology, and the discoveries that were made at that time and the records that were established at that moment can be still useful today. And of course, what they discovered was that this vast continent is enormous, and that set about the challenge of understanding it further and using scientific and technological advances to better understand the continent of Antarctica. Shackleton and Scott were using those technological advances, and it might have been through very basic petrol-driven tractors and things, for example, which didn't work out too well, but that's a good lesson to learn. They were trying to understand why they didn't work out particularly well. They might also have been using hot air balloons. So the first aerial photograph of Antarctica was taken in the Scott and Shackleton combined expedition in 1906 or 7. And they had a hot air balloon with them. So amazing that they were able to do that. Tethered, didn't go anywhere. So it was tethered to the ground. And we've been adopting technology to better understand Antarctica really since that moment. So all the way in the post-year era between the wars, but especially after the Second World War, with the moment in history around the International Geophysical Year in 1957-58, where the whole world that had been at war 15 years previously got together to establish measurements of our planet with a specific focus on better understanding the Antarctic continent. Part of that whole process of the IPY was to go back to South Pole, the first time South Pole had been visited since Scott had left it 50 years earlier, and the Americans set up a base there, Scott Amundsen Base, which now exists. So the legacy of those very early footprints, the first footprints in Antarctica in these places, we used and learned from those and built what we now establish as bases all around the continent.
Yes, and of course, Base A at Port Lockroy was one of the original British bases for scientific exploration in Antarctica. Has that produced any of the long-term data sets that have sort of been feeding into the work that you and your colleagues have been doing?
Well, there was a number of bases that were first developed by early explorers, like Port Lockroy, like Hut Point and Scott Hut as well. These are places where the remarkable new science of understanding Antarctica first began. They were taking meteorological observations, oceanographic observations, biology. These are the sort of ground zero of many Antarctic scientific disciplines that we're so grateful for today. After the IPY, geophysics really took control on understanding the Antarctic continent. In the first way, we used seismic sounding to measure the thickness of ice. We basically had no idea how thick the ice was in Antarctica. We kind of knew it was a single continent, a huge continent, and we knew how elevated the Antarctic ice sheet was, but we didn't really know how thick it was. So to do that, in the 1950s and then in the 1960s, you had to use seismics. So what you had to do with a seismic experiment was to drill a hole and put an explosion on the bottom of the hole. And then next to that, drill another hole and put the seismometers next to that. And of course, it takes about a day or so to drill both holes down to about 50 meters. Once you set it up and you let off the charge, you get very accurate information about how thick the ice is. And then you pack it all up and then you put it on a skidoo or a transporter of some kind, and you go to the next point and do it again. In the late 1960s, another technique came along called radio echo sounding, which works in exactly the same way as seismic sounding, but rather than use sound waves through an explosion, you use radio waves. And if you mount the radar on an aircraft, which can fly at like 200 kilometers an hour, and you're pinging off radio waves multiple times each second, the rate of data acquisition of ice thickness and therefore basal topography in Antarctica improved overnight by 5 orders of magnitude. It was one of the most profound advances in Antarctic discovery, almost certainly the most profound advance in Antarctic discovery that we had in the 20th century.
And that means in terms of the mapping of the actual ice and the continent underneath, all of that?
Yeah, I think probably a similar advance happened as a consequence of the satellite era and being able to get imagery and measurements of the surface. But to get information about what's underneath the surface, you still need radio echo sounding. And all that was established in the 1960s. And we're still using a very similar technique now to chart what's underneath the ice and the vast continent that exists buried, hidden underneath the huge Antarctic ice sheet.
Just so that I understand the technology, you described seismic sounding. So that's when you drill a hole and put an explosive at the bottom, which explodes and then sends sound waves through the ice down to the bottom, which reflects off the bedrock. And depending on how those sound waves come back and what speed they come back at, you can get an idea of the material that it's been passing through. But as you say, it's very slow, right? It's very laborious, very difficult to do. And with radar, you just sort of fly over an area. I mean, given that you must still be doing this now, still mapping, is it just that the radar technology is getting better and better? You have to keep doing these surveys to improve that data. What are you learning each time you fly over and do these surveys?
It's a vast ice sheet. And when you think about having an aircraft flying a geophysical transect, a straight line across the ice, we started doing it in the 60s, all the way through the 70s, been working on this for 50 or so years. We've still not got a detailed appreciation of the topography of the Antarctic continent. We kind of appreciate the general shape of the continent and where the mountains and valleys largely are. But it's the details that actually matter. If we're trying to understand how the ice sheet flows, then you can't do that with a 20-kilometer approximation. You have to understand the fine details of that continent to get it right. And we're still quite a long way away from doing that. We've actually not got a systematic survey of either the Antarctic or the Greenland ice sheet bed. And the reason we need that is because we want to understand how both the ice sheets in Greenland and Antarctica are going to be changing because of fossil fuel burning and global heating. And we need models to do that. We need computer models. And computer models need as a fundamental input bed data. And so the better we can describe the Antarctic continent, the better performance these models will have. And that's urgent. We know we can do it, but we're still not at that place right now. So we're trying our best to coordinate and get that together.
Yeah, I mean, so much polar science that you're doing today is about observing long-term trends, because that's what matters in terms of trying to understand how something like Antarctica is changing and responding to the environment in the rest of the world. I'm just curious, just to link it back again to the generations of scientists who've come before you, how much of the research that was done in Scott's era and then after the Second World War, how much of that data are you still building into the models you create today?
Well, in some other subjects, it's extremely valuable. So we started to understand the geology of the Antarctic continent from the samples that were collected in those expeditions. And so they really started off of those things and appreciating that at some stage in the past, the Antarctic continent was covered by trees. It's probably about 50 or so million years ago, now recorded in the fossil record. So we understood all of those things quite remarkably from those very early expeditions. We understood where the sea ice in Antarctica would have been because that would have been noted in ships' logs. we understood where the edge of the Ross ice shelf would have been. It was called the Great Barrier by Shackleton and Scott's parties. And that's simply because they couldn't get the boat any further down because it was a 30-metre high wall of ice in the way. You can kind of crunch your way through the sea ice, but you can't get through 30 metres thick ice shelf. So they refer to it as the barrier. But we know exactly where it was from those things. And so it gives us a remarkable point in time from which to compare the situation today.
It's all useful, isn't it?
Well, it's invaluable. I mean, there's no other data point. There's nothing before it. And actually, there wasn't too much immediately afterwards, but it gives us a recognition of a point in time that we can compare things against now.
Given that your understanding of ice is still shifting and changing as the ice itself shifts and change, can you just give listeners a sense of what the role of ice is in our climate then, in the cryosphere in general in the Earth? What does it do and what do we understand its role and importance to be?
So there's two really important things that ice and the polar regions offers the global climate. First, unsurprisingly, snow is a very bright white substance. And the reason for that is because it's reflecting sunlight. So when you go to the Antarctic, you're going to need to have some eye protection because it's an extremely bright place. And you can't survive really without deep sunglasses and powerful sunglasses. And that process is doing the Earth a big favor because the sunlight is being reflected by the ice and it's being bounced off back out into space. So the more ice we have in the world, the more solar reflection there is. And the less heating occurs as a consequence. So the polar regions are like the air conditioner of the planet, right? They cool our planet down. Now, when the ice retreats, you get less of that activity. A white reflecting surface gets replaced by like a dark absorbing surface. Could be in the ocean, but it could be on land as well. Rather than bouncing that solar radiation back out into space, it gets absorbed and heats up the ocean or heats up the land. And that's the process that's driving the Arctic to roughly warm at about 4 times the rate of the rest of the planet. And in Antarctica, it's somewhere about twice the rate of the rest of the planet. And we've noticed that in the last few decades. So rather than cooling the planet down, it seems like the polar regions are acting to warm it up, or they're cooling it less effectively, that's for certain.
And so what you're getting is a sort of feedback mechanism here. So that not only is the ice melting because of rising temperatures, but because it's melting, the land essentially, or the sea changes colour, and that makes it warm even faster.
That's exactly right. And that's one of the reasons why the Arctic sea ice is retreating so persistently since the 1970s, because the less ice there is, the more heating occurs as a consequence. The other thing that the polar regions and the ice gives us is an enormous store of water held above the level of the ocean. But if that ice melts, or if it flows into the ocean and displaces its own weight in water, like Archimedes' principle, then the sea level goes up. And we are deeply concerned about the global consequences of polar change because of the global consequences of sea level rise. And we can learn some lessons from history about that and understand where we are today in regard to sea level. So we've had about 20 centimeters of sea level since industrialization, since around about 1850. And you might not think that's particularly much. Half of that 20 centimeters, so 10 centimeters, that's come because the oceans have got warmer. And as the water warms, it expands. And so the sea level goes up. The other half is because of the glaciers that are melting, not necessarily Greenland and Antarctica, but the sort of 300,000 glaciers that exist all around the rest of the world. But here's the thing. Today, the contribution that Antarctica, the Antarctic ice sheet, and the Greenland ice sheet is making to sea level rise is greater than those 300,000 glaciers.
In terms of how much is melting from those places, you mean?
The contribution to sea level rise, absolutely. And it's also greater in combination than the oceans getting warmer and expanding. And that's a worry because historically it hasn't been the case, but from now and now on is the ice sheets that are going to be responsible for sea level change. And it's concerning because when the ice sheets get involved, you stop talking about centimeters of sea level change and you start talking about meters of sea level change. So the whole of the cryosphere, the Antarctic and Greenland ice sheet, if they all melted, sea levels could go up by about 66 meters.
We're not saying that's going to happen imminently, though, sure.
No, that's the potential. That is like the ultimate potential sea level rise on our planet, if it all melted. 300,000 glaciers all around the world. If they all melted, but you don't melt Greenland or Antarctica, the sea level goes up by about 30 centimeters. The Antarctic ice sheet is a colossal, giant store of ice. And the Greenland ice sheet's pretty big as well. But I mean, the big giant is the East Antarctic ice sheet. It's absolutely enormous. And if it starts to change and puts its ice and water into the ocean, the sea level rise could go up. Now, it's quite possible that in this century, we will get more than a meter of sea level rise. But it won't necessarily stop at 2100. It can keep going after that. And it's entirely possible we could have something like 3 meters by 2150. 3 meters of sea level rise, that puts many low-lying Pacific nations in peril. It puts places like the Netherlands in peril. The Fenlands will become Fens again, in that situation. The Scilly Isles, I mean, there's so many places that will be challenged by 3 meters of sea level rise. And what I'm telling you is because the Antarctic ice sheet is changing, it is possible that might happen in 100 years. And so are we talking about the Netherlands only having 100 years left? It is a possibility, but that's under a very high emissions scenario, incidentally like the one that we're currently on. But if we reduce our emissions and we stop global warming, the positive consequences of doing so are almost immediate. And we can reduce those very high-end sea level scenarios, stopping Antarctica reacting to unabated emissions of greenhouse gases and the global warming that occurs as a consequence. We can avoid that by getting to net zero as quickly as possible. There are some things we can't avoid. Sea level is probably going to continue to go up, but by retaining it in the sort of centimetre, tens of centimetres level is a lot better than introducing meters of sea level rise into our future.
Hello, I'm Camilla Nichol, the Chief Executive of the UK Antarctic Heritage Trust. As a charity, we work to preserve and protect Antarctica's unique heritage. From the wreck of Shackleton's Endurance and the historic huts of the early pioneers to the amazing discoveries in climate science. Our mission is to inspire more people to discover, value and protect this precious wilderness. If you enjoy what you hear today, please do consider supporting us. You can share this podcast with others, or you could visit our website to make a donation. You can play a part in Antarctica's future by making a gift towards our conservation efforts. Visit ukaht.org or search for the UK Antarctic Heritage Trust. Thank you and enjoy the rest of the show.
Discover awe-inspiring Antarctica with HX Hurtigruten Expeditions. Kayak through the icy landscape and see penguin colonies and humpback whales up close on this all-inclusive adventure. Search Travel HX to find your 2025 expedition cruise. Conditions apply. HX. Change the way you see the world.
Talk to me a bit about the ice sheets in Antarctica and how they're actually structured. I mean, if you just look at Antarctica on a map, you might see pictures of it. You see that it's covered in ice, of course, and there's ice in the sea around it. And the ice on the continent is many, many, many kilometers thick. But can you just describe for me the ice world around Antarctica? And then tell me also about where the melting is going on, which you've just warned about, and where it's accelerating, where you're worried.
So as a consequence of all the radio echo sounding that have been done to date, we know quite a lot about the shape and form of both the West Antarctic ice sheet and the East Antarctic ice sheet. And I've got to tell you that they are crazy, these places. So let's deal with the West Antarctic ice sheet. It is called a marine-based ice sheet. So it's an ice sheet and it's grounded on a bed, but in places, the bed is 2.5 kilometers below the level of the ocean surface. And that's just insane. There are parts of the Antarctic ice sheet edge, the margin, which are hundreds of meters below the level of the ocean surface. And so much of Antarctica around its margin is not terminating on land, it's terminating in the ocean. And it's not atmospheric heat that's melting the West Antarctic ice sheet. It's ocean heat that's melting it, which is deeply concerning. Today, just hypothetically, you were to say to a glaciologist, which bit of the Antarctic ice sheet would you be most worried about if it started to lose mass? Well, it turns out that's the bit that is losing mass. And it's around the Amazon Bay area, Thwaites Glacier, Pine Island Glacier. That's the bit of the Antarctic ice sheet that is about several hundred meters below the level of the ocean at its margin. And as the ice sheet retreats, it retreats right down to 2.5 kilometers below the level of the ocean. The Thwaites Glacier, often called the Doomsday Glacier, the reason it's called that is because it's losing mass. But as it loses mass, it's not contained within a sort of topographic valley like some other glaciers are. It's basically going to expose the entire West Antarctic ice sheet to further melting, i.e. it'll drag down with it the whole of the ice sheet. And with it, that's 3.5 meters worth of sea level change just in that glacier. And that's why we're worried about that. Now, in East Antarctica, about 2/3 of it is on land. But there is another third of Antarctica, like West Antarctica, that is, the bed is suppressed below the sea level. And it too can be regarded as a marine-based ice sheet in those places. And it too is losing mass in the very place that you would be most worried about as well. And so the West Antarctic ice sheet is a serious issue, but it's only 3.5 meters. I mean, only 3.5 meters. It's pretty bad, right? 3.5 meters of sea level. If the East Antarctic ice sheet starts to move as well, Totten Glacier itself is the place in East Antarctica that is losing mass, has a catchment that is bigger than the whole of West Antarctica. So if the East Antarctic ice sheet starts to change, I mean, it's a huge consequence, negative consequence, I gotta tell you, for our planet.
What is the sort of natural movement of the ice in these places as well? I mean, the ice is moving anyway on the continent, isn't it? It's not static. It's not a sort of frozen solid cube, is it?
So the flow and form of the Antarctic ice sheet, I mean, they're huge, and it's been around for a long time. The East Antarctic ice sheet could be 14 million years old. And the same sort of processes have been going on that time. So a particle of snow on the surface in the middle of the ice sheet will get buried, and it will go deep down into the ice sheet. So the further down the ice column you go, the older the ice gets. And at the bottom of the ice sheet, it could be like 1 million years old or so. But there's also a lateral flow of ice as well. And that's driven by the deformation of the ice. But it's also driven by processes operating at the bottom of the ice sheet. Because if the ice sheet gets wet, then the ice can start sliding. And if there is sediment underneath the ice and it too gets wet, it basically doesn't have any strength, right? And so the ice just sort of slips over it like a banana skin. And where it starts to do that, the ice can really speed up, not meters per year, like it will do in the center of the ice sheet, but hundreds of meters per year, like it can do at the edge. And the flow of ice is organized from the center to the margin by these very well structured rivers of ice called ice streams that just work like rivers on the surface of the planet. They're fed by tributaries and they coalesce together in a trunk and they end up coming out. So 90% of ice that's discharged around Antarctica is in ice streams. And so it's the ice streams that we're really worried about.
At the bottom of the actual ice sheets themselves.
Yeah, they're at the edge, but the processes that's driving the flow is all happening at the bottom of the ice.
I mean, we should sort of talk about climate change head on. I mean, you've talked about it in a few of the answers already, and it's kind of something that sort of lurks in the background whenever we're talking about ice or specifically Antarctica, and it's so important. And when it comes to narratives and stories about climate change, usually people hear about the North Pole. And the South Pole has been kind of largely looked over when it comes to climate change issues. And in some senses, if you're interested in climate change, you think, well, Antarctica is kind of protected because there's so much ice there. This is all starting to change, though, isn't it?
Well, it's a very interesting point. Sadly, the Antarctic continent is changing, and it's changing as a consequence of our society and the burning of fossil fuels. And over my career, over 30 odd years, we've started to notice that and appreciate it more. When I first started in glaciology 30 odd years ago, it was exciting, and Antarctica was a place of discovery, and it still is, right? Those things are still true. But what we've learned since then, it was probably true then, but what I've learned personally is that the Antarctic continent is changing, and it's changing rapidly, and that's speeding up. The Antarctic continent is losing 6 times more mass to the ocean than it did just 30 years ago. So in my career, over that time, we've noticed through satellite observations, the largest ever heat wave experienced on Earth, that's in terms of its deviation from the temperature that it should be, was in 2022, in March 2022, in East Antarctica, where the temperature should have been about minus 50. The temperature actually was about minus 12. That's like 38 degrees centigrade warmer than it should have been. That's the largest heat wave recorded on Earth. So that happened in Antarctica. In 2023, Antarctica experienced the lowest level of sea ice that it ever has done. And that's a real concern for reasons that we mentioned previously in terms of the reflectivity of solar radiation back out into space. Because if the sea ice isn't there, then it's the ocean that will be absorbing that solar radiation, and that is starting to happen.
And just to make clear, when you say sea ice, you mean the ice that has left the continent and is floating on the sea, but also during the winter, the Antarctic winter, the sea around Antarctica will also freeze at the surface as well. And essentially the continent doubles in size at that point, in most cases.
Yeah, absolutely. We're talking about the enormous cover of very thin ice, about a meter or so, wrapped around the Antarctic continent that grows in the winter and shrinks in the summer. Quite naturally, it does that. But what we've seen in March of 2023 is the lowest level of sea ice that we've ever had. And that continued across the entire year as well. So we're extremely worried about that. I mean, there may be some people that tell you that's just a fluke and it's just chance, but actually we're starting to see records broken all the time. These are records that were previously 1 in 100-year type events. And you're in trouble when the next time you break a 1 in 100-year record is the next year. It doesn't feel like it's a 1 in 100-year record anymore.
It sounds like the alarm bells are ringing. And in fact, you were talking about the records. I mean, 2023 was the lowest sea ice. And you said it's of massive concern, but actually the previous record was 2022. So it's not that the 2023 sea ice low was once every 50 years. That happened the year after.
Well, there is variability and there is natural variability. And of course, that is fine. But there's also a signal of global warming and the effects of global warming. And what we're seeing is that that signal is far greater than the variability.
You've been to Antarctica quite a few times in your career. I imagine you'll probably go again. In the times that you've been over your career, have you noticed yourself some of the physical changes that we've talked about? I just wonder if you can reflect on that a little bit. What have you seen that's changed in that time?
Well, I've been to Antarctica 3 times, and those 3 times are sort of within a 7 or 8 year period. So they haven't sort of extended across my whole career. I've rather been aware that field observations are really important, but I've never personally been driven to go to Antarctica. I've been interested in the continent, and I know that at certain stages you've got to get there to do the science, but I've always been driven by the science. I've always been driven by a better understanding of the continent. Getting field observations is critical, and so where those are necessary, that's a good time to go, but never for its own sake.
And I think it'd be interesting to know, when you have been there, what do you take away from those expeditions and those sorts of trips? Of course, the science is the most important thing, but there must be a sort of visceral, physical aspect of it as well, which you must think about.
Well, you'll never find anybody that has been to Antarctica without being profoundly affected by what they've seen in terms of this otherworldly place, which is still pristine, remarkable, and different to anywhere else on the planet. Full of history, scientific history beneath your feet, of course, and in the hills and things, knowing that on the horizon, a place that no one has ever really been before, uninhabitable if it wasn't for the luxury of heated cabins and tents and proper clothing and things. This is a remarkable place, and it's a proper privilege to have spent a large part of my career analysing and working on it, and a total privilege to have gone there several times. It is a place that's changing, sadly, and that's the other thing that we've started to realise. This isn't static and isolated and somewhere else on the planet that's not being affected by what we do, our society. It is changing, and we're learning about that change more. And as we learn about it further, we appreciate how serious Antarctic change is and will be for the rest of the planet. And that's really what drives us and motivates us to get a better handle on what's happening in Antarctica and appreciate how we can avoid the worst case scenarios of sort of unabated emissions of greenhouse gases, accelerated global warming, and a significant reaction of the Antarctic ice sheet to those things that will lead to meters of sea level rise in this century and in coming centuries that will be very, very difficult for us to be able to deal with.
Yeah, you can't put that sea level rise back, can you, into an ice sheet? Once it's done, it's done.
But we can avoid the worst of it. And that's the important, we have choices to make. You know, if we are understanding the seriousness of this correctly and recognizing that in a century, 2 centuries, 3 centuries, there are meters, many meters of sea level change that are likely to happen with unabated emissions. It's a choice we can make today to stop that from happening, that scenario.
I wonder if I can run another thing by you, though. Other people talk about other technological solutions to these things. There's green energy, of course, to stop carbon emissions as we make the transition towards non-fossil fuels and non-fossil fuel sources of energy. But people also talk about ways of changing the environment or protecting ice sheets or throwing particles up in the atmosphere to reflect sunlight. Is there anything in there? Do you think that it's just pie in the sky?
Yeah, sadly, there's nothing in this. It's an irrelevance, really. I know it's getting quite a lot of traction and discussion.
People must ask you about this.
Yeah, so I've actually coordinated a scientific paper with 40 other authors on this, pointing out how unlikely it is possible that any intervention, physical intervention into the polar region will actually help with the global crisis that we're facing. Decarbonising is the only way forward for our planet, and anything that says you can achieve it through another route is a myth, and it's dangerous, in fact.
So would that be your message to listeners who are thinking about what they can do when it comes to keeping Antarctica frozen and stopping all this potential danger, is focus on the things that you've been told already, which is net zero, it's about green energy, all those things, reducing carbon emissions, basically?
Absolutely. We know what we have to do. And we've known about it for decades. We need to decarbonise and we need to get on with it.
Just final question then, Martin, because I think that's a good point to end on. Why does Antarctica matter to you?
Well, it matters for a number of reasons. Firstly, it's a beautiful place, and it's been an absolute honour and privilege to have spent some time in the continent, but also to work on it for all the years that I have done. And it's been remarkable. And I've been involved in some amazing expeditions and made some interesting scientific findings. And I just feel very lucky to have been in a position to contribute and help. But it's also important to me because I know through the work that I've been doing and reading many other people's work as well, that the Antarctic continent is changing. And it's changing rapidly and increasingly. And we need to do our best to avoid it changing in a way that will severely damage our planet and our children's and their children's and those that come after them, their lives and livelihoods, as it surely will with unabated greenhouse gas emissions. So the best thing we can do is to get on board with decarbonising. And if we did that, we'll stabilise the climate relatively quickly within 10 or 20 years, and we can save the worst case scenarios of unabated emissions and the reaction to all of that. That's our best. It's our only way forward. And the longer we leave it, of course, the more damage we'll do to our planet and to our future, which makes it urgent. It means that we've got to get on with it right now.
Martin, thank you very much for your time.
No, my pleasure.
Thank you for listening. A Voyage to Antarctica is brought to you by the UK Antarctic Heritage Trust and made possible by support from HX Hurtigruten Expeditions. To find out more about our guests and how you can support the Trust, please head to our website, www.ukaht.org, or find us on social media. If you enjoyed this episode, please don't forget to follow and rate us wherever you get your podcasts. It makes a huge difference to us. Next time, Henrietta Hammond will be telling me the gripping story of Apsley Cherry Garrard's The Worst Journey in the World, which remains one of the greatest works of travel and adventure writing to this day. A Voyage to Antarctica was presented by me, Alok Jha. Theme music is by Alec Hughes, and editing and additional music is by James Stickland. The show is produced by Jessica Norman. See you next time.